Welcome back to International Finance. I am Andy Kim, your Dr. Finance. This video, this is for math refreshers and economics refreshers before we delve deeper into option pricing model for foreign exchange futures options, FX futures options, like call options and put options, right? What are we going to talk about? Over here, we're going to talk about risk neutrality of economic agent. Why risk neutrality? We learned something about risk aversion before, but why? Okay, I believe you've taken basic finance course where you discussed this option pricing, perhaps in your investment class, right? Some of you must have taken some derivatives class before. So in that case, you don't need to look at this video. But this, we're going to go through those basics of option pricing model. There, you remember binomial option pricing model, okay, as well as Black-Scholes, but a binomial option pricing model that relied on risk neutral probability, right? Which enables you to discount cash flow at risk-free rate, which makes your life a whole lot easier because you don't have to worry about how to model risk premium for your call option or other assets, right? So how can we bring this risk neutral probability, risk neutrality over there, right? The agents being risk neutral kind of things. What is that concept, right? We're going to talk about that initially. And then we're going to do some kind of math refreshers because not only discrete time discounting, but also continuous time the discounting we will have to worry about. That gets into your Black-Scholes model, right? Natural log, e to the power of RT, big T, wow, R, hey, e to the power of what the heck, you may say. But we're going to go through, and then step by step, you will be able to, digest those things together with me. And then before we go into options in FX market, we're going to briefly go through binomial pricing in call options on stock market. Okay, why? Because FX, right? We're going to interpret those options on FX from using the tool of option on stocks, right? Call options on stocks. There was some dividend component in it, and then all these kind of discount rates and things like that. And then we're going to translate those components in foreign exchange market using the framework of stock-based option pricing model. So get ready for this. Let's go. So we refresh our memories about the expected utility theory, starting from von Neumann Morgenstern, right? So what was that about? Here, the vertical axis is utility, and then here you have final stage wealth, right? What is it about? It's about risk taking, right? Risk taking. It's about utility, right? Utility that you can expect when you take some gambles, right? Uncertainty being involved, right? Flipping coins, right? And then head and tails, half and half probability. You never know what's going to happen. But once those head or tail happens, then you know how much of a wealth you're going to have at the end of the day, right? So let's say you're flipping a coin. Head, you get like 100, and tail, you get nothing, right? Tail, you get nothing over here, and head, you get 100 over there, right? Half and half probability, I said. But usually the people, right? Well, how much would they feel happy when they get $0 as opposed to $100? Let's say it's like this, right? A bit concave for most of the people, right? We call it risk aversion. The concavity itself tells us about the risk aversion of the economic agent, right? What does that mean? Well, first of all, okay, the degree of getting happier is diminishing, right? No surprise. But what is interesting about this is this risk premium, and then certainty equivalent that we're going to talk about, right? The thing is, the utility this coin flipping gives you, okay, the utility the coin flipping, this gamble gives you, right, is the probability weighted average. Probability weighted average of these two utilities over here. This utility of up, right? And then this utility of down, wealth down, right? And then how much would you be happy about it? Well, that's the probability weighted P of utility up plus 1 minus P. That P is your probability of having up, head, and tail probability of utility of wealth in your down stage. Okay? That is going to be your expected utility. Expected value. Remember that? Probability weighted things. Ah, yes. Now, these utility function, the shape, right? The utility function shape depends on the functional form that you assume. Okay? The functional form that you assume. Now here, I assume the concave utility function like square root of wealth or something like that. Okay? The utility will be like this, something like this. Now, here, right, if you do the probability weight half and half of these two, it will be half, like just over here, right? So the linear, it's a linear combination. It's gonna be on a straight line like this. Let me use a different color over here. So it's gonna be on this expected utility will be in the half point over here. Half. This guy will be as happy as this, right? Expected utility. That's this point. Why not this point? This point is something called certainty equivalent, right? Certainty equivalent. Well, instead of taking this coin flipping, right? Give me something risk-free so that you can make me as happy as this coin flipping gambling. Okay? I don't want that gambling stuff. I want something for sure given to me. The sure amount that can make you equally happy to this coin flipping gambling. That certainty equivalent amount is this guy, CE, over here. Right? Certainty equivalent. And then what you see over here, let me draw this one. Over here, this is expected wealth, which is your probability of wealth up plus 1 minus probability of wealth down. Here, it's a coin flip, okay? 50-50 chance, and then your wealth in each different stage. Coin flipping, head or tails. Head or up, right? Let's say down, like this, right? So this is your expected wealth, right? And then, so this is certainty equivalent amount that we call it. The thing is, the more risk averse you are, the smaller the certainty equivalent would be. Okay? I hate so much, I hate to take risk, take risk anything, right? I want a safer life. Okay? 소확행. So much so that if you give me a small bit of amount, I would be equally happy. Right? Some people will have this kind of more concave shape as opposed to other people, right? Certainty equivalent will be so much smaller, okay? A lot more risk-averse person Okay. Well, on the other hand, if you are more risk-seeking than this guy, then your certainty equivalent will be somewhere over here. Okay, so that your expected utility function, the utility function will be like somewhere going over here like this. Not concave at all, right? It is slightly concave, right? Getting less and less risk averse. Now, so this gap between your expected wealth and certainty equivalent, this gap, right, has to do with your risk aversion, okay? And this is called risk premium, RP. Yes, risk premium. So that's RP, risk premium, right? For purple, risk premium, okay? If you hate to take risk, you charge more risk premium. Remember that cap and beta times Rm minus Rf? That beta times Rf minus Rf had to do with this risk premium. It was a risk premium, right? The more risk averse, the more risk premium you charge, right? That's the idea. Now, this is risk averse agent's utility function. But there are some people who are more risk-seeking, not just this degree, the green line, but to the degree of what? Let me draw with a this line over here, like this. There are natural-born gamblers in this world. Ha! Funny, right? And these kind of guys, right, love to take more risk. If he's taken off the chance of getting into gambling place, he will do whatever, that's risk seeker, risk lover, right? Their risk premium is negative. And then there are some people who are risk neutral. Risk neutral is like this straight line over here. Straight line. Okay? The guy is as happy as the dollar amount he gets at the final stage. Right? $10 you get, $10 worth of happiness you will get. 10 times the wealth you get, 10 times the happier. N times bigger wealth, N times bigger happiness. That's risk neutrality, this straight line. Okay? Can the people be like that? Well, we can assume that kind of things. We can model that one with straight line function. Okay? You're going to see the example there. Now, so we move down over here in the diagram. You see what I'm talking about over here. Expected utility function. Yes. Now, let's go. Expected utility, well, theory is based on this one. Let's go through 3 different forms of function, utility function. Now the first one is so utility function of risk-averse investors, whose utility function is just like this one, square root function. The second one is a risk-neutral investors utility function, which is just a linear function, straight line, 3 times W. Okay? Why shouldn't it be 1 times W? Didn't you say exactly as much as, but what I'm saying is proportionately in the linear fashion. Okay? Let's just put in this number 3 over there as a coefficient. The third one is risk-seeking investors or gamblers, natural-born gamblers, which is square function, wealth squared like this. Okay? Convex function, concave function, and the linear one. Okay? Now, risky decision making, the coin flip, 50-50 chance, right? Head you gain 100, tail you gain nothing. Just to simplify our discussion. Okay? And this expected utility should be like this. Just as I showed you before, it should be nothing but the probability weighted average of those utility at the end of each state of nature. Head, tail, right? And then, given that this is a coin flip, it has to be half and half. Now, you see this utility of 100 times half plus another half, the other half times utility when it is 0. Now, thankfully, due to the simplicity of this utility function, you realize that the utility that you get in the tail state would be 0 all the way down. What matters over here would be the head state, right? For simplicity of our calculation. For the 3 different investors, let's see. The difference between expected wealth of a coin flipping and the certainty equivalent is related to the risk aversion. I told you about this one, yes. First one is risk-averse investors, risk-averse agent, whose utility function is a concave one, like square root of wealth, right? And coin flip, 50-50 chance, head, you gain 100, and then tail, you get nothing, right? And then expected utility of this gambling will be 5 according to this utility function and the expected value, right? Then how about his or her utility at the expected wealth of 50, right? You know, 100, 0, 50-50 chance, expected wealth will be the average, which is 50. If, 50 is given risk-free, how much would he or she be happy? That's 7.07, right? And you see that is this part over here. You see this picture, right? In the diagram over here. 7.07, which will be higher than your expected utility in this coin flipping gamble, right? Why is this happening? Because this guy is risk averse. So he wants something risk-free better than risky. He will be happier. She will be happier if it is given risk-free. The other things being equal, same thing is given to him or her. Give me risk-free, right? That's this. Now, didn't you talk about certainty equivalent? Yeah, that's the next one, right? He would be happier if 50 was given with certainty instead of taking such risk. The second one, certainty equivalent, is here in the last bullet point. Expected utility of 5, right? Expected utility of 5 is when you have a wealth of 25 over here, okay? Wealth of 25. You know, this 5 was the expected utility of this coin flipping gamble, right? And then this one, 25 is given risk-free for sure. Then he would be equally happy, indifferent between coin flipping versus taking its money for risk-free. So this is certainty equivalent. The difference between these two is called what? Risk premium. All right, risk premium. And then you remember in your intermediate corporate finance class or basic finance class, right? The required rate of return or discount rate had two components, which is risk-free rate and risk premium, and you modeled this one in CAPM with market risk premium times beta. And then if you go through multi-factor model, you have other factors included: market size, book to market, and momentum, and many different factors, right? That's nothing but decomposing this risk premium in different economic model, right? But for now, what you have to remember is this risk premium part, which is this purple, right? Purple part as a whole, this part, okay, this part. Now, risk neutral investors is the second agent that you want to talk about, whose utility function is 3 times W, the wealth at final stage. The risky decision making, 50-50 coin flipping, 100 you gain, and if you just head, tail, nothing. Expected utility will be half of it, right? Half of what? Well, 3 times 100 in your head state, and then 0 at tail state, right? 2 different states of nature, probability half and half, average of it, 150. That's your expected utility. That's this guy. Okay. Now, of course, the picture is kind of, this diagram over here is kind of misleading because it has to be different slope, right? Instead of based on the square root function, it should be really like 3 times, like something like straight line over there, and then it has to be somewhere. That's what I'm saying, right? And then how about his or her utility at the expected wealth of 50? Well, that is 50 times 3, 150. Wasn't it the expected utility, the same number? Yes, that's what risk neutrality is about. Your expected utility is the same as the utility at the expected wealth. Okay, he would be indifferent between receiving 50 for sure and taking that gamble. And then 150 should be equal to utility at your expected wealth, and then it's a certainty equivalent is equal to your expected wealth in this gambling. So the risk premium should be what? Risk premium should be 0. What would be the risk premium? I told you about this, 0. And this guy is as happy as the expected wealth without any risk premium, right? So only if, right, if you are living in this in the risk neutral world, that everybody is risk neutral, then we don't have to worry about how to model this risk premium. We can only live with this risk-free rate in discounting everything. Wouldn't it be convenient? Because we've been having so much trouble modeling this risk premium. God knows why. So that's why. And the third agent is risk-seeking investors, like square function, right? Risky decision making, coin flip, 50-50. Again, 100 and 0. Expected utility is what? 5,000 in this number, right? And how about his or her utility at the expected gain of 50? Well, that is 2,500, which is way lower than expected utility. Give me some more gambling. That's what's happening right now. I hate something for sure. I want something more risk-taking. Natural-born gamblers, right? And he would be sad if 50 was given for sure instead of letting him do the gamble. And then, right, you do the math, certainty equivalent, right, is way bigger, right, than his expected wealth. What can you tell about his risk premium? It's going to be negative number. Anyway, now, in a risk-neutral world, all investors are indifferent to risk. Investors require no compensation for risk. Wow. Is that possible? In a parallel world, right? The expected return on all securities is the risk-free interest rate in this world. So if you can model anything and then using this risk-neutral agents in this world, life will be easier, right? Can we do that? Is the next, I think it's going to be the next video, right? So thanks for watching.